This time we have 17 points. 17 points inside an equilateral triangle. This is the harder version, right? Let's just draw it here. So we have this equilateral triangle, side length 2, let's say. And we have 17 points. We want to say that two of them will come close to each other by a distance less than 2, less than half. Right? So last time we picked 5 points, say, and we showed that two of them are at a distance less than 1. And the idea was to dissect the figure in a way that 2 points come in the same piece, and then they are. So how many pieces did we dissect last time? So last time when you have 5 points, right? And you want 2 of them to come close, then obviously you divide it in 4 parts. That's the natural way, right? So we just did it in the most. Also, the division was the canonical division, triangulation, like this. And these are again equilateral triangles of side length 1, and we said that 2 of the points come inside it. Inside one of the piece, we don't know which piece, but if we have 5 points, and 2 of them will come in the same piece, and these 2 will be at a distance less than 1. This was simple check. This time we have 17 points. So the question is, how should we divide the triangle into 16 pieces? How do we do that? Step 1. So it's natural that we want to divide them into 16 pieces, because in the end it's like 2 points, something, 17 points in total. So if I would have asked you to show that there are 4 points which are at a distance less than 1, then that's a different question. Then you would have to think different. We want 2 points to come, so we want there to be just 1 less number of pieces than number of points. 1 less pigeonhole than number of pieces. So how do we divide the triangle into 16 pieces? What's the most natural way to do it? Exactly. Yeah, just make further triangulations. Dicentric, these are called dicentric subdivision. So again, the answer is to do it as Sana said, just the natural thing. Just do the most natural thing. New. Just do the most natural. And also divide this by 2. So yeah, just do it. They will same line. So this is done. Once again, 2 points will be close to each other. There will be 2 points which come inside the same triangle by Pigeonhole Principle. Let me decide. There are 2 points in the same piece. And so their distance will be less than half, because side lengths of these triangles are half. So all these variations that we are doing, okay, these are the steps on which you have to build. Okay, because it's impossible to do, you have to spend. But like this particular thing, you kind of see the theme. Okay. The idea is to, now in harder questions, you have to dissect the figure in more interesting ways, or you have to do more casework sometimes. Some of the cases which look true will not be true. Some casework or some other variations. And then this builds on later probability theory, tiling theory. It just goes on and on. Okay, so this is a very. So is this clear to everyone? Let me just then I just give a variation of this. So you can try. So then the variation is that show that there exist 4 points, okay, which are all with distance less than 1 between all 4. It's important that if something is not clear, you clarify it. It's the, as I said, you are stepping stones on it. I don't want you guys to fear these kind of questions, because once you stop fearing, then you can learn on most of this on your own. One thing is you shouldn't fear. You didn't get lost again a new trick again. No, you can see that it's natural ideas. Yes, so between any 4, I should say. Between, so there will be 4 points such that there will exist 4 points among these 17 such that any distance between these 4 points is less than 1. Okay, like this is less than 1, 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 this is less than 1. Okay. So last time what we showed is that there are 2 points with distance less than 1. But now I'm telling you that there will be 4 points. There will be 4 points so that in those 4 points, any 2 points you pick, their distance is less than simultaneously. So basically, official 4 points are in a small piece, and that's it. Now, in this picture, it's half, right? In this picture, it is half. Is that right? Because you see, this is 2. Right? So that is clear, right? Because this length is 1. Yeah, this length is 1. This length is 1, and then this length is half. This is next step. Is it? So don't mix this new version. In this new version, you may have to do something else. Is it? Yeah. So I'm just saying that this triangle has side length half. That's clear, right? Because there's 2 steps. One step smaller, it became side length 1, then side length became half. And that we used. But now this different problem I'm giving this, I'm not saying that you have to use the same time. That's you don't know. I don't know what you have to use. That's problem 4. Okay, yes, maybe. Yeah, that seems to be right. Okay, but yeah, so you guys think about this. Okay, so today so far we have just done variations, variations and harder versions of what we did last time. Or sort of. But maybe let's use this principle to prove a fact, okay, which all of us know, but maybe we don't know how to prove. So maybe this time I can say an application. To periodicity periodicity in decimal expansion. What I'm saying is, like, when you take a rational number, when you take a rational number p by q, so you can take any rational number, you can take like 5 by 7. Right? When you take it, so when you take its decimal expansion, so what is the decimal expansion of 5 by 7? 0. Yeah, someone? 714, and then again 714. Or so then 28. So this is not a good question, but if you can do it fast, then you can tell me. You can do it in 857. Aha. Okay. Then it's repeating again from the start. 714. Yes. So this was not such a good example, but you can see that it still repeats. Okay. The point is that when you take any rational number and you expand it, it repeats. Yeah. In the decimal expansion, there is a repetition. So have you guys given this a thought? Why is there a repetition? That's the fundamental question, right? This was on my mind for a long time. I didn't know how to prove this in 11th standard. Even then, maybe even now, I have to see. But why is there a repetition? Same dividend. You mean the number 5 is going to come again? This 5 by 7, this 5. Okay. Okay, in the long division thing, you're saying. But that doesn't always happen, right? Yes, and also sometimes the repetition, like the first few terms may not repeat, right? So you can always think of some rational numbers like this, and you can just convert this to a rational. Okay. So you can take something like 2, 2, then you can take 3, 3, 3, 3, right? This is also rational. I mean, you can create a rational number out of this, right? And you will see that. So the first two terms do not have to repeat. That is, they don't. So it doesn't have to repeat right from the beginning, but sometimes there will be a period. So why is that period there? Like, why is there this periodicity? So that's what we have to think about. Okay, so you guys have given a reason, but that's based on the understanding of the long division. But then how do you prove that the long division gives the right answer? Is that right? I mean, how do you trust the long division process? But still, let's say that we trust it. Let's see. Then let's try to reason. So if you just remind me, it might have forgotten long division. Uh, and it's also a little um, difficult to explain it in general, right? Using the long division process. How do you explain it in general? So if you have Q and if I have the P, yeah, it's very strange, right? To explain it like this today. But let's explain it through this example maybe. But really the proof has to come in a different way, where you don't have to rely on long division, and also it's difficult to prove things from the long division process. Long division is good to give us the answer quickly. But so basically we had this 7, and then we have this 5. And then how do we do this? So this doesn't go, so we put a decimal into this. Then we take this. Let's see. We get the 1. Then what happens? Then we just continue this. Maybe so maybe you have to put this 0. It's a very strange rule, right? Why do you have to put this 0? Okay, it works, but yeah. Okay. 7, and then this 3. Okay. The point is that this 5 turns up once again in this case, right? This 5 turns up again at some point. And when it turns up, the situation just repeats again, right? Because you have to just write 50 and then everything just repeats all over again. Okay. But why should the 5 turn up again? That is the question. And the answer is, well, it doesn't have to. And in this case, it does. But what is the fundamental reason that the 5 comes again? Because the remainders that we are getting, right, they are always less than 7. So try to understand this, right? These are all remainders. This 1 that you're getting is a remainder, right? You're taking the number 50. You're subtracting the largest multiple of 7 that you can. You're leaving with the remainder. Again, you have 10, you subtract 7, the largest possible, you get 3. These remainders are all less than 7. Not equal to even. When we can be from 0. Yeah. You see, the remainders are all less than 7, from 0 to 7. Yeah. So in every time you do the subtraction, maybe that is what Ishana was saying about subtraction, but when you subtract, the numbers that you get as remainders, they are always less than 7. So after 8 steps at most, they will repeat. 2 remainders will be the same. So it's not that the 5 has to come up again. In this case, it does, but it doesn't have to always. Okay, when it does not is also a very interesting question. So just take a minute and think about this one. Okay, let's not rush it. Just go over this. Take more example and try. Do this for yourself for 2 minutes, and then let's see. And if you have more, if some questions popping up in this, ask me. Yes, that's a very good question. So the problem, so the reason why this question comes up and the answer to that question is difficult to give because we really don't know what this decimal expansion even means. You see, the meaning of decimal expansion is given by long division process. Yeah, but that's very strange, right? It should have something to do with the rational number 5 by 7. Right? You start with 5 by 7, you run this arbitrarily strange process which we have been taught since, I don't know, and we get this answer. So how can anybody question the rightness or wrongness of this long division? You cannot. Is that you see what I'm trying to say, right? You cannot question this because really there's no meaning to the answer. The meaning to the answer is given by the process. The whole thing is messed up in some sense. That's why we don't have this. But this tells us that we should ask a more fundamental question: is what is this decimal expansion? So that you should think about. Then you can answer this. So given, so maybe I should, so this equality that we just write is very strange, right? I should say, what is the relation, or rather more simple, what is the relation between, let's say, this and this? We are always told it is equal, but then what does it mean? What does the right hand side mean? If you think about it, we don't know. I mean, up to if you think just in the long term, we don't actually know what that means. Very sad thing, actually, in some sense. So think about this. All of you should think about this. Then only you can ask the question, right? What is the relation? Why are they equal? What does it even mean to say equal? So what do you mean write it as a fraction? Yeah, that's the first step. Yeah, you're saying that this means this, something like that, or okay, no, but then also okay, uh, right, right. Yeah, so that gives a semi meaning to the decimal, right? So that defines the decimal partially, but still, how is an infinite decimal defined is not very clear. That's still, yeah, so just, yeah, so just think about this, then you can go into this one. Currently, I'm not going because then we will end up in different place. All right, but if we assume that the long division gives us the right answer, then this is what happens. That you have any number. So if you take a number, so can you guys give me an example of a fraction where the period doesn't repeat right from the first block, doesn't repeat right from the first term? So I want an example where you get some non-periodic part, and then there is this, then there is a period. You see what I'm asking, right? Can you give an example of such a decimal? Oh, sorry, such a fraction. So no, pi is not 22 by 7. Okay, 22 by 7. Okay. Okay, okay. So you're saying that no, 22 by 7, I don't think that happens. Okay, no, but it for 22 by 7, when you say, then I will take 22 by 7 as 1 by 7. The 21 by 7 I'll forget. That's a 3 that, okay, that you can always do. I'm saying 0.7. Okay. But in 1.7, what's the decimal expansion of 1.7? So that's 1. 2. 8. So this is not what I want. Right. I don't want it. I want a fraction in which repetition will always happen, but I want something in which repetition happens, but not from the first number. It doesn't the first, I mean, not from the first number itself. So I suppose you can take something like 2 by. So what is 2 by? Okay, 2 by. So you can take 2 by 15. What is the thing for 2 by 15? Or maybe don't take 2 by 15. This page or something. Yeah, let's say 2 by 15. What's the? Just quickly tell me something. What's the thing of 2 by 15? No. 0.133. Yes. Yeah. 0.13. Okay, got it. Yeah, you see. So why is it that in this case, you see this is not in the, obviously after that the repetition is simple, but the first term is not in the repetition. Okay. So that's what I'm trying to say. That you will take at most 15 steps and the remainder will repeat. So let's assume that this long division process is correct and so on. So this is the last thing to do. We have just 15. So we get this 20 and then we get this one. The point is that the remainders are all less than 15. Then we put this. So then we have this 45 and then 5. So the point is that you see this. So initially it was 2, yeah, but then, or rather it's 20, but the 2 is right. Then you have 5, but then 5 comes again, and if 5 comes again, then obviously 5 will come again and again and again. Right? So the point is that once a remainder comes again in the process, and it will after at most 15 steps. So you can also tell the length of the period. Another wonderful thing will be at most it will be 15. In this case, it's just 1. Okay. So I suppose that what I tried to do is to show you that if you are doing that, writing the decimal version of a fraction, then there will be periodicity. Okay. Is that point clear to everyone? But along that, we have understood seen many more things. The length of the period is at most this much. For some fractions, initially it doesn't, and it doesn't occur in the periodicity, but after some point it does. Now it's the later on you will learn, and you can think and see this now, try to see it now, is for what kind of fractions does the periodicity start right from the get-go? And for what kind of fractions does the periodicity, is there an initial delay and then there is a periodicity? And how could you figure out the exact length of the periodicity? That we are not able to do till now. Exact length now, without actually doing the calculation. Those are the new questions that come up. but they are not in the realm of pigeonhole principle, right? Pigeonhole principle is all about showing that something exists. Okay. At more, how much exactly that is? Those questions we think. I suppose we'll just stop today. Okay. So we've done these variations. So maybe once again, I think last time, did I send you guys anything to try? I had sent, right?